Hello, and welcome to another lovely session of Civil Engineering with Tanya J. Laird. I am the aforementioned Tanya J. Laird. This video is the 16th lecture in our wood design series. This is a follow-on lecture to the previous video. In this video, we will be seeing a few examples of how to apply the LRFD time effect factor and the ASD load duration factor to structural wood design. As in the previous lecture, the music today comes from the artist Unheard Music Concepts from their album The Lasso of Time. A link is included in the video description. Alright, so let's consider this example here. Determine the critical load combination for a wood tension member required to resist a dead load of 80 kips and an occupancy live load of 30 kips. So what we're going to be looking at is LRFD design today, well, with this example anyway. And so let's see. So basically with this, what I'm trying to do is I'm just trying to illustrate how the load duration factor and how the time effect factor, how they interact with load combinations. And so I'm not going to be running through a full design of this given member. I'm just exploring which load case or load combination in this particular instance would be critical. And you'll see what I mean in a second. So let me just label this. Let's say, let's do this. First step, let's calculate our load combinations. And since we only have two loads, a dead load and a live load, we're only going to need to worry about the first two load combinations from ASC 7. So I'm going to call these, I'm assuming these are axial loads, so I'm just going to call these P1 and P2, corresponding to the first load combination and the second load combination from ASC 7. And P1, that's just going to be 1.4 times the dead load, and I'm going to report this in newtons rather than kips to be consistent. And I'll copy that and get my second load combination. And this is going to be my 1.2 dead times 1.6 times live. So we have a first load combination of 112 kips and a second load combination value of 144 kips. So just looking at the load combinations, it seems like, actually maybe I'll just write this. Based on load combos, number 2 seems to control. Let's see what happens though when we add the effect of the time effect factor. Add the effect of the time effect factor, really? Okay. So, or when we consider the time effect factor. There, I've managed to use it, describe it without using the word factor twice. Okay, so step 2. Implement time effect factor. And it's always good to put a reference, and this is NDS and table N.3.3. And let's go ahead and jump on over there and take a look at that again really quickly. So our time effect factor here, notice it's going to, it varies based on the load combination, and it's our lambda value here. And it's key to remember that this is going to be multiplied by our resistance. And I'll explore that back on the SMath sheet. And so for the first combination, we're going to be using a lambda value of 0.6. And for the second one, we are going to be using one of these. And if you saw in the problem statement, or if you remember from the problem statement, it said that we're going to be looking at a occupancy live load. So for the second one, we're going to be using 0.8. So if you think about the way LRFD load combinations work, they're always going to be something kind of like this. You have, let's say, let's do the traditional way. Let's say the gammas. You'll have gamma times a summation of loads. Let's see, where's my sigma? Okay. Sigma of p-values. And this has to be less than or equal to, actually I have less than or equal to sign. I'll just go ahead and use that. And then that has to be less than or equal to a phi rn. So if I have my phi value, where is that here? Phi Rn. Okay, so what does this mean, of course? Well, we have gamma, which is our load factors. Actually, that load factor should be inside the sigma. Let's put that where it belongs. So this is just a little bit of review of basic load combinations. We have our the summation of the load factors. That's basically what I've calculated here, and that has to be less than or equal to the summation of our resistance factors times our nominal resistance. Now, if we actually wanted to calculate the resistance capacity of this or verify a member was adequate or something like that, we would need to consider all of the factors that are actually contained within this BRN. However, notice all I was asked to do was to find the critical load combination. And since in terms of design, all of the other, like, there's a lot of things that go into a member design. Like there's your nominal capacity, there's your nominal resistance from the NDS supplement. There's, things like, there's things like moisture factor, there's size factors, there's a whole bunch of factors. And again, we'll get to those later in the series. All we're looking at today is the time effect factor. So what really matters here is that the key to remember is that baked into the nominal resistance is the time effect factor. So the time effect factor is something that is multiplied, or the nominal resistance is going to be basically a lambda times something. You're going to have your time effect factor times some things. And those things are going to be your nominal stress times maybe a cross-sectional area and then times a series of factors. But if all we want to do is figure out which load combination is going to control, we got to think carefully about what actual mathematical quantity we need to consider. And because we're ignoring all of the other factors, what we can say is that the critical value is going to be, if you haven't already figured this out, it's going to be P divided by our lambda. Because our lambda factor is multiplied by our resistance, if we want to figure out what load effectively controls, we bring that lambda factor over to the other side. Rn being the same, or Rn in this case being P. So for each of these, we're now going to calculate a P over lambda value, and the greater one of those is going to actually control the design of this tension member. So I'll go ahead and get two lambda values. Lambda 1 corresponding to our lambda for our first load combination, again the 1.4 dead, is 0.6. And again, that's from NDS table endpoint 3.3. And then our lambda 2, I got that as a comment. Lambda 2 is going to be 0.8 because it's not just live load, but occupancy live load. And so then we can calculate our two values, or our two coefficients, or not coefficients, our two critical values. So P1 divided by lambda 1, that's going to equal that many newtons. And that's way too many decimal places, but that's bugging me out. So let's put that as maybe one decimal place seems a little more reasonable. And then we'll do the same for our lambda 2. So now we see why I chose these particular values. With the time effect factor included, the first load combination, or I'll just be too natural to say, number 1 controls. Number 1 controls. Again, because we multiply the lambda, or the time effect factor, by the nominal resistance, if it's less than 1, it's going to decrease our nominal resistance, which is really the same as dividing the load the load value by that resistance, the factored load by that, not by that resistance, by that factor. Again, if you have a factor on the resistance side of the equation, dividing by that factor on the load side of the equation is equivalent. So this factor, both of our factors here happen to be less than 1, and if they are on the right side, they're going to decrease the resistance, and if they're on the left side, they're going to increase the load. And so if you're just trying to determine which load combination is critical, these two are equivalent. So what we see here is that, and again, obviously, usually you won't get values that are just so perfect that they change between two load combinations. I deliberately chose these values to produce this effect, but without the time effect factor, the second load combination clearly has a higher value. But when you factor in, or when you consider the time effect factor, the first load combination will actually control. Because again, factoring in the effects of time, because wood behaves differently over time, because wood behaves differently over time, the dead load case, load number 1, will actually control. Alright, let's now consider the second example. A line of bolts must be able to resist a dead load of 50 kips and an impact live load of 60 kips. Without considering the effects of load duration, the bolts have a design capacity of 100 kips. Are the bolts adequate? So in other words, for this 100 kip value, I have already gone and calculated, I've looked up the nominal reference stress, I've applied all the other design factors, I've multiplied by whatever geometric property is applicable, etc., considered both bolts and tear out and all sorts of other things. So ignoring all that and just focusing just in on the effects of time right now. So let's compare our two, here we're going to have to consider two different load combinations. Well, actually, are we? Because consider this here. We're dealing with ASD here, and if I look at the ASD, if I consider the ASD load combinations, let's go over to ASC 7 and take a look. So, let's see here. ASC 7, 4 load combinations for allowable stress design. Since we only have dead and live, only the first 2 load combinations will control, so we don't need to worry yet about wind or seismic or anything like that. So we only need to look at these first 2, and additionally, what else? There are no factors applied. It's simply the sum of the 2. Okay, so let's go back to SMath now. All right. So we have a dead load of 50 kips and a live load of 60 kips. So our overall load, I'm just going to call that P. I'm assuming this is tension. Oh, let's define that. As D plus L, and it's that many newtons, or if I transform that to kips, 110 kips. Although we could have just added that up in our heads, of course. Okay, so it seems at first that we have a problem. The dead and live load are 110 kips, but our bolts only have a calculated capacity of 100 kips. So if I put a little note here, without considering the time effects, or the effects of time, the connection seems inadequate, or the bolts seem inadequate. But as we learned in the previous, the theoretical video preceding this, we saw that because of many reasons, wood exhibits lower strength for longer duration loadings. Okay, so what we then need to do is, let's go ahead and, actually, you know what, I think it might be, if I wanted to really do this proper, I probably should actually split it up. And you'll see why, because that'll allow us to apply 2 different time duration factors. So I'm going to call this one P2, because that was the second ASD load combination. and P1 would just be the dead load. And that would equal that many newtons, or this many kips. 50 kips, and of course that makes sense. Okay, so let's see here. So what we now need to consider is the effects of time on load, or actually on resistance, I should say. So let's go on over back to our PDF, and we'll look at the NDS, and we want to look at table 2.3.2. So looking here, we can see that for dead load, our load effect, or I should say our load duration factor, is 0.9, and for impact live load, it's 2.0. And so those are the two different types of load that we have. So let's consider this. Let's go back to our SMath sheet. So I'm going to first consider, maybe I'll do something like this. Check first load combination. And our CD, I'll just label this as the load duration factor. And I'll put a reference of NDS table 2.3.2. For this first load combination, our load duration factor, C sub D, and I'll give that a little subscript 1 for the first case, that's going to be equal to 0.9 because that's the only, that is the only load we have in that particular load combination. And so then let's go ahead and calculate the resistance. And this is going to be, well, actually, I should probably put another term perhaps here. I could call this resistance without load duration factor. And I can just call this maybe R equals 100 kips. All right, so now we need to multiply our resistance times this load duration factor. So our resistance is going to be R times our CD1. Again, because as the problem statement said, without considering the effects of load duration, bolts have a design capacity of 100 kips. In other words, I've already done a full calculation of all of their capacity, considering a myriad of factors, except the load duration factor. And so all I have to do to calculate the final capacity is just multiply by the load effects, or the load duration factor. And so that's going to be that many newtons, or actually, let's see here. Or I can translate that to kips. 90 kips. So let's go ahead and set up a comparison. I can just say P1, or just P1 equals that many newtons, or kips. And just for completion's sake, I can just say that is less than or equal to this. So we are adequate. Again, as long as our, because this is our load combination. Let's see, load combo 1, and this is our design capacity. Okay, so we have that. And again, that was just with the first load combination. So we're fine there, because 50 is less than 90, so we are adequate. Now I'm just going to copy this and modify it for the second load combination. So CD2. Now this is where it gets interesting. So let's go back, let's take a peek at that table again. Okay, so let's go back to this table. And if I look at impact live load, which is what I have, I would say that the CD factor is 2.0. except you always have to be on the lookout for various caveats. And if we look here at footnote 2, as we discussed in the theory video, load duration factors greater than 1.6 shall not be used in the design of structural members pressure treated with waterborne preservatives or fire retardant chemicals. That's not really applicable here. If I had something that was being designed for soil contact, it probably would. But what is important is that load duration factors greater than 1.6 shall not be used in the design of connections or wood structural panels. Bolts. If I go back to the problem statement, this is for a series of bolts, and the only thing you typically use bolts for is a connection. Well, I suppose there might be some maniac out there who's just, putting bolts into timbers just for fun. Maybe there's some engineer out there who just likes to fill their buildings that they build out with superfluous bolts just to have a sort of like a steampunk vibe or something. But anyway, if we assume a sane use of bolts, that is probably being used for some sort of connection. So let's go ahead and say, okay, well, P2, that is equal to 110 kips, and our load duration factor is not 0.9, but 1.6. Again, we might think that we could use 2.0, but because this is a connection, we're not allowed to take a value greater than 1.6. And so the resistance, it will now be multiplied by 1.6, and we have a resistive capacity of 160 kips. And then just putting in the applicable values here, we see that load combo 2 is less than or equal to the design capacity. Actually, I should say probably here for load combo 2. Design capacity for load combo 1. So you can see here that when you start taking into the effects of time, figuring out which load combination is critical can actually be a bit tricky. And that's because at first it seems that the dead load in this particular case, or not the dead load, but it seems at first that this connection is inadequate, but based on the high value of this live load. But because it's impact live load, we're allowed to use a relatively high value of this load duration factor, and that means that that is multiplied by our resistance. We multiply the resistance by this. That ends up giving us a greater capacity than our load combination. So we are actually valid, or we are actually adequate for both the first and second load combination, even though just looking at this, 50 plus 60 is 110, and the resistance is 100. It seems at first that no, this connection will obviously fail. But again, the key thing to remember is that the values, the reference design values in the NDS are calculated for normal duration loads. In other words, loads with a expected lifetime or expected occurrence time of 10 years over the course of a structure's lifetime. And something like impact, that is an instantaneous load that happens over a fraction of a second. And so we've learned in the previous lecture that wood exhibits greater strength for loads that are applied over shorter and shorter periods of time, and lower strength for loads that are applied over longer periods of time. And because of that, in this particular case, it's almost like it was deliberately designed that way or something. But no, that couldn't be the case. Anyway, in this particular case, yes, it turns out that when considering the effects of load duration, that will actually make this connection adequate when just looking at the raw values of the loads and the capacity before load duration was considered, it would not be adequate. All right, and I think that'll do it. All right, I think that will do it for today. This video was just a few examples seeing how to apply the time effect and load duration factors from the NDS specification. If you have any questions, please leave them in the comments below. If you found this video useful, please like, comment, and subscribe to make the robots happy. If you want to help make content like this possible, see the link to our Patreon page in the video description. Regardless, we'll be back soon with another video in this series. I look forward to seeing y'all then, and as always, thank you.